Okay. So let's continue. Okay. So it's augmenting data structure. Okay. One thing I want you to know is that some set of slides that I'm teaching this semester is slightly different from what I taught last year. Okay, my habit is like I because our textbook is like this thick, right? So we usually can only cover maybe about 1/3 of this textbook, okay, in this class. So my habits, I would change a few chapters every time I teach a course, okay. So that's the reason this year, okay, the content, okay, is slightly different. For example, last year I didn't teach red black tree. I didn't teach this augmenting data structure either. Okay, so what is augmenting data structure? Okay, we are going to talk about dynamic order statistics and interval tree. Basically, these are highly related to red black tree. Okay, so so basically, okay, what is the dynamic order statistics? Okay, we actually talked about something similar to this one earlier. Okay, remember given some numbers, we want to find, for example, the ith rank. Okay, so it's ith smallest number from these numbers. Okay, assuming they are all different. Okay, 就是我们叫叫什么，也是叫什么 order statistics。OK， 就是在那个 quick sort 之后的那一章。OK， after we cover the sorting algorithm, we talk about that. We remember we even talk about how we can guarantee, the complexity is the worst case complexity is it's not n squared. Okay, we will break the numbers into a group of 5. Delos trick. That is covered in the midterm, is that right? 在期中考就已经 cover 那个了，如果大家还没有完全忘掉的话 ，OK。So this one is similar. This one is similar. So this order statistics select IS and order statistics rank XS. Okay. So it's in a dynamic set S. The select is we want to return the ith smallest element, okay, in this dynamic set S. The rank XS is given element X in this set, we want to find the rank for this node X, okay, in this set. Okay. Previously, we use the trick we use is the partition, the random partition stuff. Okay, we could use because I also told you this binary search trick can be used for sorting, and the basic idea of this binary search tree, when it is used for sorting, is very, very similar, okay, to quick sort. It's just the comparison order of the comparisons happen differently. Remember, I told you about that. So obviously, we could use it. Utilize that to solve problems such as select and the rank. Okay. To be specific, we could use red-black tree, not only like a binary search tree, but also a very specific red-black tree for set S. Okay, but keep a subtree size in the nodes. Okay, first, why do we use red-black tree? Because if it's just like a partition, if you do not put any constraint, if you do not break the node, break number into a group of 5, the worst case scenario is going to be n squared, right? Okay, if you want to find a rank I number from n different numbers. Okay, same thing. Okay, if you use a regular binary search tree without any constraint, then the worst case scenario is not guaranteed because the tree may be skewed, right? 就它可能会歪到一边，很坏的情形的话 ，OK。But so we can only guarantee average case performance for a regular binary search tree. But if you use red-black tree, we know because the height of the tree is guaranteed to be log n. So, and we know red-black tree, the maintenance and construction, pretty much everything, the performance is, the analysis, okay, or the cost is similar to binary search tree anyway. So it would be nice if we can use a red-black tree for this dynamic order statistics purpose. Okay, so this idea to maintain the subtree size in a node is like this. We store the key and the size in the node. Okay, the size, the key basically just key. Okay, that's the key in the binary search tree. Okay, just regular key. Okay, and the size indicate the number of nodes in this subtree, including this node itself. Okay, so let me give you an example. Okay, here, okay, of course I'm using the alphabets. Okay, A, B, C, D. So you can see, it is obviously A, C, D, F, H, M, N, P, O, P, Q. Sorry, P, Q. So it's it comply with the order of the alphabets, but we just intentionally use these letters to avoid confusion. After all, this is the first time we talk about this order statistics tree. So you can see the keys are these letters, but each of the node is also associated with a number, which indicate number of nodes in this subtree. For example, for leaf node, okay, it's 1. Okay, for example, for node F, okay, it's 3 because for this leaf subtree we have 3 nodes. Okay, for this we have 3 nodes, and for the whole thing we have 9 nodes. So we store 9 here. So it's easy to understand, right? Right? So far so good, right? Okay, but we do not draw the color here. It's just, but I want you to keep in mind that this is essentially a red-black tree. Okay, it's just you just treat it as a binary search tree. Okay, just keep in mind this binary search tree has some, we have property to maintain. Okay, and the cost, okay, for the construction, for the height of trees, are guaranteed, okay, to be very good. Okay? And obviously, okay, the size of a node is the size of left subtree plus size of right subtree plus 1. And because of that, remember, for red-black tree, we have leaf nodes, right? Leaf node does not store key, right? Okay, so yeah, we also have leaf node, but we do not draw it here. Okay, so for leaf node, I mean, obviously, I mean, it doesn't have so the upper half is is nil, or it does not contain the key, but the lower half of the leaf node, remember, we need to store the number of nodes in this subtree, right? So for consistency, we will store 0 in the leaf node, okay, for the size. Because you see, okay, the size of x is going to be size of left subtree, left child, okay, plus size of right child plus 1, right? So for example, for this one, your left child is well, it's a leaf node, right? Right child is also a leaf node. So for this both leaf node, okay, the size have to be 0. So 0 plus 1, in order to be consistent with like the size there, right? So far so good, right? Should be pretty easy. So once you have this order statistics tree, how do we perform the selection? I mean, we are only going to talk about the select, okay? The rank is the opposite, and so it's kind of like a concept is similar, so I will not go into the detail, okay? But I mean, it's just like we talk about insert, okay, in the red-black tree. For the delete, I want you guys to check by yourself. And for select, it's very, very simple, okay? Given like x and I, okay, we want to find the ith smallest element in the subtree rooted at x. Okay, so first, okay, we assign, okay, k to be size of the left child plus 1. This size of left child plus 1, what is that? That basically is the rank of x. Because, I mean, in order traversal, you will finish all the nodes in the left subtree, and then the node itself, right? So the node itself is like the rank will be, number of nodes in the left subtree plus 1, right? 就是你这个 node 你的 root 的，或者说你现在这个点的它的 order 它的顺序，它第几个，是不是它的左指数的数字加1嘛？因为你们会 in order traversal， 你应该知道 in order 左边的走完，再走到这个，对不对？因为这是 binary search tree 嘛，它的那个走的顺序就是它的那个大小嘛，根据它大小。So it's like so this is the rank of x. So if this k is exactly what you are looking for, the I is what you are looking for, the rank you are looking for. If I is equal to k, then you just return x. I mean, that is exactly what you are looking for. Okay. Otherwise, if what you are looking for is lower than k, then you will go to the left child, and with I, still the I, you are going to call this OS select recursively. 你就是在左指数里面找第 I 个大的。Okay, that's pretty straightforward, right? Okay. Otherwise, okay, if it's not the case, in other words, the I is greater than k, so in that case, you are going to go to a right child, right subtree. You are going to find like the I minus k largest one in the right subtree. That's it. Very, very straightforward. Let's use like an example here. This is exactly like the OS tree, okay? That, I mean, example that I just gave you earlier. So let's assume we want to find the rank 5 from this tree, okay? So I is 5. K is, what is K? K is the left child size plus 1, right? So left child size is 5. 5 plus 1 is 6, so K is 6. So K is larger than I, so you go to the left child. And I stays the same, I is 5. So what is the K here? I mean, that's like a left child size plus 1, so it's 2. So I is now bigger than 2, K, so you go to the right child. When you go to the right child, okay, you are going to call this OS select recursively by, you know, I become 5 minus 2, so it's 3, I is 3. So you are going to find like the third largest one in this subtree. And what is the K here? K here is like a left child size plus 1 is 2. So again, I is bigger than K, so you go to a right child. So now you want to, I is 1. And this K is 1 too. So, well, great. I mean, so we found it. So H is the 5th element in this, well, binary search tree or red-black tree, whatever you want to call it. Should be very straightforward, right? So any question with this? Okay, good. So you can see that, okay, red-black tree can be used for like different purposes. And, you know, this always select, if you use red-black tree, okay, the running time is guaranteed to be, in the worst case, you know, it's the height of the tree, right? And the height of the tree in a red-black tree is guaranteed to be log n, so it's big O log n, okay, if you use a red-black tree for the underlying binary search tree. Okay? So far so good, right? Okay, so let's continue. So why not keep the ranks themselves in a node instead of subtree size? Okay, because the rank are harder to maintain when the red-black tree is modified. Remember, we are going to use the red-black tree. And remember, this is called dynamic order statistics. So in other words, like the difference between this order statistic and the previous order statistic we are talking about is that we have insert, we have delete involved. Okay? And because it's I mean, the red-black tree is easier to deal with insert and delete. But previously, I mean, when we talk about red-black tree, insert and the delete, I mean, basically we talk about like, yeah, I mean, not only we need to maintain the binary search tree property, we also need to maintain the red-black tree property, those 4 properties, remember? Okay, and we need to do like, you know, not only like color changing and maybe like rotations, you know, to get to make sure like the red-black tree property is maintained. So now, okay, with that additional information, the size, okay, how do we maintain this property? Okay, the size is easier to maintain, okay, compared with the rank. Why? Let's just look at insert, okay. For example, okay, if you want to, I'm sorry for this, this doesn't look good, okay. So it's supposed, I should create two slides. Like it's like before the insertion, okay, this is actually like, before the insertion is actually this one. It's actually this one. Okay, So we have 9 here, we have 5 here, 3, 1, all these numbers. I mean, to represent the size. But once you want to insert k, okay, obviously when you want to insert k, it falls here. It falls at this location. So now it's 1, right? So basically, you can change the, this insertion, you can just first change the size, okay? When you are searching the location to insert k. Okay, so because k, you are going to go from here to here to here to here and to here. So you can see this one change from 9 to 10. This one change from 5 to 6. This one change from 3 to 4. This one change from 1 to 2. And then you put the k here. Okay, so on the way to insert this k, you can modify the size. I'm not done yet, because you need to, recurring doesn't change the structure, but the rotation will change the structure, right? Okay, we are going to talk about that too. But okay, I just want you to understand first, okay, this size can be modified very conveniently when you insert a new node, okay, which is not as easy if you want to maintain rank, because rank represents the left child plus 1, right? The left child plus 1. Left child size plus 1, and the rank, okay, for example, for this node, it's actually not 1. The rank is actually 10. The rank is actually 10, right? So if you want to maintain rank for each node, it's not that easy, okay? It's not that easy. Okay, you can check it out by yourself. And then we also need to make sure, in the rotation, this size is maintained, okay? So, well, for recurring, there's no effect on the subtree size because we are not changing the structure of the tree anyway. But in the rotation, yeah, I mean, for example, here, okay, let's say we are doing, we're doing a right rotation here. So you can see, say the size of this subtree is 7. The size of this subtree here is 3. The size of subtree here is 4. After rotation, this one becomes 16. So you are going to copy this value because C is going to replace E, right, to become the root of this subtree. So this is going to change from 11 to 16. C becomes 16. And for the left child, it remains to be 7. For right child, it's E. But the E, the value of E is now has to be different. It's going to be, this is 3, this is 4. So 3, 4 here. So you are going to add a 3 plus 4 plus 1 here. And all this operation, all this computation, again, is done locally, right? It's done locally. So it can be maintained in constant time. Okay, this is about right rotation. For left rotation, it's similar. Okay, so I just want to argue. Okay, I just want to provide this to you, the rotation. Okay, even if you include the size in each node, it can be maintained in in a very efficient manner. Okay, in the red black tree. So, in other words, okay, the red black tree insert and red black tree delete, okay, are still in big O log n time. Okay, if you are using them for the OS tree. If I'm using them for order statistics, for dynamic order statistic. Okay, in other words, like each node, you have additional size information there. So, I don't know if I can finish this lecture today. Okay, I hope I could. Okay, if I could, I would assign assignment to you, as I said, like after the completion of this lecture. If not, I'll assign the assignment next time. Okay, but I really hope I can cover, as many lectures as possible in this class. After all, like, algorithm is a very big subject. Okay, in computer science. Okay. So now you understand, red-black tree is not only can be used for like binary search tree. It can be used for like this rank, to find the rank and to do the select. Okay, all these things. It can actually have like a more applications. Okay, data structure augmentation. Okay, so one example is order statistics tree. Okay, but actually it can have many different applications. Okay, so for different application, you choose an underlying data structure that guarantee like a certain like a performance, like what should I say, like of like different operations, such as red-black tree. Okay, and you can determine additional information to be stored in the data structure. So take order statistics as an example. For each node, you are storing like a subtree size for each node, right? And then you verify if this information can be maintained, okay, without additional like complexity, without increasing the time complexity. Okay, so insert, red-black tree insert, red-black tree delete. Of course, in this insert or delete, like rotation is a big plays a big role. So you need to make sure like this. In red-black tree, like this additional property, the additional like information, the subtree size can be properly maintained without increasing the complexity. And then, you can develop a new dynamic set operations that use the information, use this additional information, this subtree size. So these steps are guidelines, not rigid rules. So in the previous one that we are talking about, we actually talk about the fourth one first, and then we talk about the third one. Okay, so it's not necessary. We don't necessarily follow this very strictly, but this is a kind of like a guideline. So you say, oh, then other than the like order statistics tree, any other applications that we can think of? Yes. Okay. So the next one is a very interesting and important subject. Interval tree. I need to first. Has anyone here taken my computational geometry class? No, right? If any of you are in my data structure, in my computational geometry class, or is auditing my class, you will learn that in my computational geometry class, I also talk about interval tree. But the interval trees that we talk about in the computational geometry is different. It doesn't rely on red black tree. But yes, it also uses a binary search tree. But it doesn't involve red black tree. Okay, so we don't talk about like to maintain like a red black tree property there. Okay, but the idea is similar. So what is interval tree? So first we need to talk about the problem. So we are given a set of intervals. So for example here, okay, we have many intervals. So interval is represented by its lower bound and the upper bound, right? Or you can say it's a low high, okay. For example, this is for this interval I, okay, the low I is 7, the high I is 10. Okay, so we are only talking about like a one-dimensional interval. Okay, I mean, to be honest, in like computational geometry, we even talk about window search, window query. Okay, so that's like not only like it's a one dimension, it's a two-dimensional stuff. But don't worry about that. I mean, you're not in my computational geometry class. But here, okay, so we have this bunch of intervals, right? And then you are given a specific interval. Okay, we are given for a given query interval. The query is also represented by interval. Okay, so we want to find interval in a set that overlaps I. There are two different types of problems here. The first type of problem, such as this one, we only want to find an interval in a set that overlaps I. Just one of them. Obviously, you could have multiple intervals that overlap with this query interval, right? Okay, so the other possible query is for a given query interval I, you want to find all the intervals in a set that overlap I. So these two are two different problems. So let's talk about the simple version first. Talk about this simple version first, and then we'll talk about like a more complicated version. Okay. So we want to only find one. But finding one is also important. It's like if you have any one in this set that has overlap, you have to make sure that one has to be found, right? Not like we couldn't find, but actually there's one interval that in your set that really has an overlap. Then this is not acceptable. If your set has any interval that overlap, you have to find one from all this overlapped interval and return that. Okay, so how do we do it? I'm sorry. So we follow this guideline. What is the guideline here? The guideline first tell us that we need to choose the underlying data structure, right? So a data structure that we could use, okay, as I have told you earlier, okay, red black tree makes a good data structure. But yeah, if you use the red black tree, the first question is, for each node we have a key, right? We have key. But for each interval, we have two values, right? A low and a high, right? We have, because you have a left endpoint and right endpoint for one interval. I mean, but the key, only has one value, right? You cannot, you can, what should I say? You can sort by one value, but you cannot sort by two values, right? So here, okay, the idea is that we just use one endpoint as the key. Okay, so if you use only one endpoint, okay, then let's assume we use a low endpoint. Can we use right endpoint? We could, but the other part needs to be modified as well, obviously. Okay, okay. So first, I just want you guys to understand we use left endpoint as a key, but we are going to store the entire interval. So this int basically indicate we store the left endpoint, right endpoint here, but the real key is left endpoint. Okay? So in the int, it means interval. So we store two numbers to indicate the interval. But for key, we only use the left endpoint, or what we call like low. Okay, low. And then we have additional information here that we need to store in the data structure, right? So what do we store? Okay, so we store in each node x the largest value mx in the subtree rooted at x. Okay, so the largest value mx in the subtree as well. So this is like for all the subtrees, the largest key, we store it in M. In the previous order statistic tree example, we store the size of subtree, but here we store the largest value. Let me use the example. This largest value indicate the, for all the intervals in this subtree, the largest, what should I say, right endpoint. Right endpoint. So for example, so for this one, you can see it's this interval is from 7 to 10, right? So we store 10. So for this one, okay, you can see we have 1, 2, 3, 4 intervals. Among these 4 intervals, the largest value or largest right endpoint is 18. So we store 18 here, and so on. So the other, I think you guys get the idea. Is it good? So far so good, right? Okay. So for this mx, this is this thing. It's going to be max, the high int x. It means like the right endpoint of what you store here. Okay. So this my own right endpoint, or the left subtree, the m of left subtree, m of right subtree. Okay, so for example, for this one, you see, my right endpoint is 18, and the my left endpoint, my left subtree my left child m is 10. So the larger one among these two is 18, right? So here it's like 11, 8, and 18. The 18 is the largest one, so it's 18 there. So this thing can be decided, by this node and its two children, right? You don't need to go any further, okay, to determine this this information, right? Right? Okay. And then, we need to make sure, okay, according to our guideline, we already finished the first step. We already finished the second step. Okay, so additional information, what additional information to be kept at each node? Okay, we say that's m, right? M, the largest value, okay, largest right endpoint of among all the interval rooted at this node, okay, in the subtree rooted at this node. So like we already decided. Finished the first step, second step. The third step is we need to verify. Okay, this information can be maintained, for modifying operation. In other words, like insert and delete. For delete, again, I will skip. For insert, I think we can easily verify. For example, say, well, actually, like all the other operations, like changing color. Again, changing color does not involve like changing the architecture, right? Structure of the tree. So it doesn't change the value of m. So the only thing that will affect the value of m is rotation, right? Rotation. So now, okay, so here is the thing, okay? So this is the, you rotate to the right, okay? Rotate to the right. So you see, when you rotate, this node becomes a root. So you are going to copy the origin value here to here. But they happen to be the same. But if they are different, then you need to copy to here. Okay? So this one becomes like a 6, 20, 30. And this part remains the same. Okay, this part remains the same. And this one becomes a right child. Okay? And this value has to become, you have to re-verify this value, okay, to be, the max of its right endpoint and its left child and right child. Okay, the left child, right child stays like that. So 14, 19, and 15, the largest value among these three. So it's 19. You store 19 here. Done. Again, this all operation can be finished in constant time, right? You only need to check the children's, and then basically like you copy the value from one node to the other, and then after the modification of the structure, you need to compute the new value for one node. Done. That's it. This is for the right rotation. For left rotation is similar. Okay, so this thing can be maintained in constant time. Okay, so in other words, after you make sure like these rotations can be done in constant time, then the insert will take log and delete will be similar. Okay, so yeah, so we could use like the red black tree, okay, without paying extra like additional like complexity, okay, for any operation, pretty much. Okay. Then remember our original goal is like you are given a query interval and you want to find one okay, one interval that overlap with it, right? Just one. So you need to develop a new dynamic set operations that use the information. So interval search, I. This I is the query interval. Is the query interval. I mean, I is not just a number, it's an interval. So it has left, it has low, it has high. Okay, or left or right, depending on what you want to use. Okay, so anyway. So you start from the root. While x is not nil. Okay, if x is nil, then I mean you go to the end. I mean like a leaf node, you couldn't find it, so you return a nil, right? You return a x which is nil. If the low I is greater than high int x, or low int x is greater than high I, then you do this. What is that? This low I, okay, what is low I? Low I basically means like the left endpoint of I, right? Left endpoint of I, okay, is greater than high int x. So it's larger than, like, remember what is the int x is currently it's a root, right? So int x basically is an interval stored in x, right? So if its lower I is greater than its right endpoint, or the low int x, low int x means the left endpoint of the interval stored in x is larger than high I. Okay, its left endpoint stored at x is greater than the right endpoint of I, meaning, okay, x does not overlap with I. Okay, if any of these cases happen, x is the interval stored at x does not overlap with I. Okay, does not overlap with I. Okay, but so let's talk about the opposite. The opposite meaning, okay, when these two clauses are both violated, right? These clauses are both violated. If these clauses are both violated, then you are not going to run the while loop, right? You are not going to run the while loop. You are going to go to return x. Why? Because if both of these cases are violated, what does that mean? It means that the I is completely contained in the interval x, right? Interval stored in x, right? So if that's the case, obviously x, the interval in x has overlap with the query interval I, so you are going to return x. It's very safe for you to return x. Okay. But if not, if this while clause is satisfied, then we know like I and int x don't overlap. We know that, as I said earlier. So if left x is not nil, so the left child of x is not nil, and the low I is smaller or equal to m left x. So whatever the m value of its left child, is greater equal to low I. I mean the left endpoint of I. That means like that means this interval, if there's any overlap, it should go to it happens in the left child, left subtree. So you go here. Okay, you go here. If this is not the case, you go to the right subtree. Okay, and then you go back to verify the while loop. Okay, you repeatedly doing that until one interval is found. Just one. I mean, when one interval is found, I mean, you may have more than one interval that has overlap, but that's fine. You return one. When you find one in overlap, that means this part is this while loop. This part is not satisfied. So you break the while loop. You return the overlap interval. That's it. Okay. So let me use like an example. So this is like a valid interval tree that we utilize the red-black tree for that. Okay, and then we assume we are doing the query interval is 14, 16. Okay, 14, 16 is our query interval I. Okay, and then we start from root, right? We start from the root. And when we start from the root, obviously you can see, 17 is larger than 16, right? 17 is larger than 16. So it means that, it means this one. High int I x, high int x is smaller than low I, right? The high int x is low int x is larger than high I. So it's this one, the second one. So that means like there's no overlap. This interval is not overlap with this interval I. So we check, the 18. We get into the while loop. We check the m left x. Okay, because left x is not nil, obviously. So we check m left x. M left x is this one, 18. 18 is larger than 14, 16, right? 18 is larger than 14, 16. So this is 18 is larger than 14. That's low I. 18 larger than the low I, the left end point of I. So we will go to the left child. So we go to a left subtree from X. What does it mean? This means that, if there's a overlap, we can find, this 17, 19, can be, because 18 appears somewhere like larger than the low end point. Here. Larger than this interval. So we may be able to find some interval that overlap here. So we go here. And then again, we check the interval. Okay, 14, 16 with 5, 11. So obviously, like the high int I, the high int I is lower than the low I. Okay, so there's no overlap. Okay, so then, okay, we need to search, okay, on, we need to check the, it's not overlap. So we need to, don't overlap. Its left child is not nil either. So we need to check like a left child n value to see if it's larger or equal to low I. So the left child is 8. 8 is not any larger than the low I. Okay, so that basically means what? That basically means all the interval in these subtrees cannot overlap with that, right? Because any interval stored in this subtree, the largest right endpoint is 8. So 8 is lower than its lower endpoint. So it's impossible for any interval in this left subtree to overlap with them. So we go to a right subchild. Okay, so now we try to check 14, 16, and 15, 18 to see if they overlap. And obviously that's that we have overlap. We hit overlap, so we return 15, 18. Right? Okay, so basically, this is like how we get this job done with that additional information stored at each node, that n value. Okay, and this code allowed us to find one overlap interval, right? Oh, this is another example. Let's look at the other example. Another one is 12, 14. 12, 14. 12, 14, the query interval, I, 12, 14, and with the same interval tree. 12, 14, well, it's, if you check with the root, I mean, it's not overlap. So we go to the left child because 18 is bigger than 12. So we go to left child. So 5, 11, 5, 11 is not overlap with like 12, 14 either. So then we check the n value of the left child. Okay, 8 is is smaller than the left endpoint. So we go to the right child. Right child 15, 18. 15, 18 is not overlapped. It doesn't. It's not overlapped with 12, 14. Okay, and then we check the left child n value. So 10. 10 is lower than the left endpoint 12. Okay, so it means that we have to go to the right. But if you go to the right, there's a nil. Okay, there's a nil. X equal to nil. So there's no interval that overlap 12, 14. So this is another example that show you, okay, that how we get this job done. So So far so good, right? So this is like a, the time complexity for this query, because we go from the root to, the worst case, we go to the leaf node, okay? And it's going to be height of the tree, okay? So it's going to be log n, okay? Because interval tree, basically is implemented by the red-black tree. Okay, so if you use this code, you are able to find one interval. If you want to list all the interval, what do? You search. Search is like the code that we use. We find one, right? Once you find that interval, you delete it. You're going to list it and delete it, and then you repeat. You keep doing that until no interval can be found. You found, a nil is returned, and then you stop. So this is a very, very simple approach. Okay. The complexity is going to be big O k log n. Okay. What is k? K is the number of overlapping intervals that you report. Okay. Because say you find one interval, say if you find like 3 intervals that overlap, okay, then basically you are going to do search 3 times. Actually, you are going to do search 4 times. 4 times. 3 plus 1, because the last one is like a failed search. And you are going to list it. It takes, not much time, constant time. Delete. The deletion, each one take log n2. Okay, log n. So again, it's k log n. Okay, you delete 3. If you find 3 interval, it's going to be 3 log n operation, right? So k log n, and that's it. So it's like basically it's k log n. Okay, and this is what we call output sensitive algorithm. Okay, this is perhaps like the first time in this class that we talk about this. Okay, a lot of algorithms, that we talk. I mean, we have talked about many different algorithms in this class, and usually the algorithm complexity is only related to the size of the problem, right? What is the size of the problem? It's n. In this case, it's n. Okay. Remember, in the sorting, is the size of problem is number of how many numbers you have, right? Yeah. So so basically, like in the past, all the algorithm we talk about is only complexity is only related to the size of the problem. But this is the first time. The algorithm, complexity involve k, where k is number of, is the size of the output. K has something to do with the size of the output. Okay, actually, there are many such like output. We call this type of algorithm output sensitive. Output sensitive. Okay, so for output sensitive algorithms, some of those output sensitive algorithms, it's like for example, like in many cases, okay, when the output is small, output size is small, you save the kind complexity, but in the worst case, it could be worse than some other method that is not output sensitive. Okay, so it's like it depends on the situation. It depends on the situation. Okay, for example, if you are given a bunch of line segments, I give you a bunch of line segments. I want you to find all the intersections from n line segments. How do we do it? Well, I mean, you could say, well, I just check if, Cn2, right? Get any pair of like a line segment. You check if they intersect or not, right? Checking if whether two line segment intersect or not take constant time. We know in high school you learn how to compute if two line segment intersect or not. Okay, you need it involve solving 那个联立方程组嘛，对不对？those stuff but in computer science as long as the computation, some of those computations may take time, but as long as it can be done in constant time, even though that constant time may be a little bit larger, at least it's not, it doesn't grow, when the size of problem increase, because you just try to compute if two segment intersect or not, right? So problem size is fixed. So it's the computation just take constant time, even though it may take some time for you to, manually compute it. 你也许用手动来，可能要花一点时间去计算，但是这个计算时间还是被当作是常数的。Okay, then Cn2, right? So it's like n squared, right? N squared. But I could tell you there's a faster algorithm out there. How? Again, output sensitive. Okay, output sensitive. I can tell you if you are not going to have too many intersections, then you can really save the time. But in the worst case, 如果说每两条线都有可能有相交，那的确你就是可能有 n 平方这么多的这个 O 的 n 平方这么多的 intersection 嘛，对不对？所以你其实并没有办法省到什么东西。但是如果说 OK 你给了 n 条线，你的 intersection 的数量其实是很少的，甚至比n 还少，那你有可能可以省，就是 there are ways to there are output sensitive algorithms that help you to compute this faster. And in reality, it is the case that given n line segments, there are not too many intersections. For example, 如果说你的 line segment 表示的是路，你另外一组 line segment 表现是什么？表示是河流。那它们的 over intersection 代表什么意思？桥嘛，对不对？路要过河流，一定是一个桥，对不对？对不对？这有没有问题？很容易接受吧？对不对？那我问同学，你有很多条路，你有可能会有很多条桥吗？不太可能，为什么？造桥贵啊。所以你看，譬如说中立不是有河吗？它不是说任何一条路都可以过河吧？你常常要绕过去，到某一条比较主要的干道过河，对不对？对不对？所以不是所有的 intersection， 就很多的应用里面给你 n 个 line segment 的 intersection 其实并不多，但是I just want to tell you, okay, this output sensitive bound is an important concept that will happen very, very often in reality, in applications. Okay, so in many applications, yeah, the output is the size of output is really not that big. Okay, so in this case, the k log n, the k could be very small, you know, but in general case, it could be large. In general case, I cannot avoid. I mean, I cannot say it has to be small. It depends on the situation. It depends on the applications. Okay. Anyway, so I'm done with this part, but I haven't finished this chapter, so I think I'll wait until next week to give you homework assignment. Okay. The rest is really just like a theorem and correctness proof. Okay, but I think I'll wait until next week to talk about that. Okay. So any question?如果没有问题，我们就下礼拜见哦。Okay, I'll see you next week. I hope by next week we will be able to go back to our original classroom. Okay, if I know ahead of time that the projector still has a problem, I will notify you guys to come here.